Hello, my name is Jussi Kuusisto. I'm a PhD student at the University of Sussex, and in this talk I will be talking about active galactic nuclei in the first light and reionization epoch simulations, or FLARES. This is work that's been conducted under the supervision of Stephen Wilkins, and it's partly a continuation from work done by former Sussex master's students Ross Denier and Hamish Garnett, and with the help of my many colleagues listed here. Here's an outline to my talk. So first I'm going to give you the brief cosmological context, then describe the simulations themselves, and do some comparisons with Eagle reference simulation, as well as explain briefly the black hole physics that go into these simulations. Then I'm going to describe the AGN in FLARES and talk a little bit about the black holes themselves, as well as the AGN properties, spectral energy distributions, luminosity functions, as well as a few words on ionizing photon production. And then finally, I will describe preliminary work on AGN impacts on host galaxies, as well as tease some upcoming papers from our group. So in this talk, I will be talking about galaxies and AGN in the reionization epoch, so in the first about 1 billion years of universe's history. And the relevant questions for us there are: when and how did the first galaxies form, and how did these reionization processes progress? And crucially for this talk, what is the role of AGN in galaxy formation and reionization? So FLARES itself is a suite of resimulations of 40 regions picked from this huge dark matter only parent box. This schematic is showing the comparison between the parent volume and blue tide simulation, as well as the Eagle 100 megaparsec box. The FLARES simulations were introduced in Chris Lovel's paper from last year, so check that out if you're interested. And the regions themselves were picked based on the density compared to the average density in the parent simulation, and resimulated down to just below redshift 5 with full Eagle model hydrodynamics. And this visualization gives you examples of those FLARES regions. As you can see that there's a high density region here, and as you progress along this schematic, you get to lower density regions. So this simulation strategy allows us to combine the regions using a weighting scheme, also described in that Chris Lovell et al. Paper I mentioned. And it allows us to build, for instance, luminosity functions out of the combined volume of all of the regions. So as an example of that, on the right here, I'm displaying the UV luminosity function of FLARES galaxies in solid lines at redshift 6. Compared to the Eagle reference simulation luminosity function in dashed lines. And as you can see, the FLARES luminosity function actually probes into the extreme bright end of the luminosity function. And on the top panel, you see the numbers of actual simulated galaxies in the simulations that are going into the bins in the luminosity function. And as you can see, FLARES simulates a lot more galaxies than Eagle does, and this is especially relevant for the highest luminosities here. So we are probing a larger effective volume than a traditional period box would. And to put that increase in another way, here's the cumulative number of simulated galaxies as a function of their stellar mass for both FLARES in solid lines and Eagle in dotted lines, and color-coded by redshift. And from this we can see that the FLARES combined regions at redshift 5, for instance, has above 10 to 10 solar masses, has about 20 times as many galaxies as there are in Eagle. And this increase is even more relevant to even higher masses, and therefore also relevant for the most rare objects in the universe, such as massive AGN host galaxies. and also complements the upcoming generation of wide area telescopes. Now, the black hole physics in FLARES also follows the Eagle model, in which black hole seeds of mass 10 to 5 solar masses are seeded into galaxies with halo masses of 10 to 10 solar masses or above. So because the seed mass is below the resolution limit of the simulation, we use subgrid recipes for this, and FLARES specifically uses the AGN DT9 parameters. The black hole accretion rate is tied to Bondi accretion, and it's limited by the Eddington rate. So as an example, I'm showing here the fraction of galaxies hosting a black hole as a function of galaxy mass, stellar mass, at different redshifts. So you can see how that relation slowly creeps up towards all galaxies at the massive end having black holes seeded into them. On the right here, we see the stellar mass functions for galaxies in dashed lines, as well as all galaxies in dashed lines, as well as black hole host galaxies in solid lines. And on the bottom on the left, we see the number of black holes as a function of black hole mass for the simulation. And on the right, on the bottom, we have the redshift 5 black hole accretion rate as a function of stellar mass. And what's plotted here is the median in the solid line, and the shaded region around it gives the central 68th percentile range. So that brings me to the actual active galactic nuclei in FLARES. So first, I'm going to show you the luminosities, intrinsic bolometric luminosities of the AGN. So this is calculated from the black hole accretion rates. So it's essentially a fraction of the energy released in the accretion of matter onto the black hole is released as radiation, and that gives us the intrinsic bolometric luminosity of the AGN. So I'm plotting here again the median luminosity for AGN, and the shaded region is giving the 68th percentile range as a function of stellar mass of the host galaxy for the epoch of reionization redshifts, so from Z5 to 10. And another recipe that goes into modeling the spectra of the AGN is AGN temperature. So this is the so-called big blue bump temperature of the spectral energy distribution or SED of the AGN. And it's calculated from this equation over here, which is an equation of both the black hole accretion rate as well as the black hole mass. And the figure here shows in column map the temperature of the AGN, and the black dots show the flares as a function of both the black hole accretion rate and the black hole mass. And the black dots here show the redshift 5 FLARES galaxies where they lie on in this space, and the dashed line gives the Eddington limit. So once we acquire the bolometric luminosities as well as the temperatures of our AGN, we use Cloudy to model AGN SEDs for a range of different temperatures, and then scale them according to the AGN bolometric luminosities. And this allows us to calculate corrections going from bolometric luminosity to, for instance, the contribution of far ultraviolets, or optical emission, or ionizing emission for the AGN. And that's what's plotted here. So essentially the fraction of luminosity in far ultraviolet, optical emission, as well as ionizing emission for AGN spectra as a function of the AGN temperature. So that leads us into the luminosity function. So what I'm showing here is the intrinsic bolometric luminosity function for both AGN in dashed lines and the host galaxies in dotted lines. and then the combined object or the combined luminosity function, where I've just summed the AGN contribution and the stellar contribution together to investigate how much the AGN actually are affecting the luminosity function. So here we again have those for multiple different redshifts, and as we can see, the number densities at the extreme bright end of the intrinsic bolometric luminosity functions are slightly elevated due to the AGN. And this allows us to also ask the question, do the AGN outshine their host galaxies? So what I'm plotting here is the median of AGN bolometric luminosity to the stellar bolometric luminosity of the host galaxy as a function of stellar mass, and the shaded region gives us the 68th percentile range around the median. And this is log of 10 of that quantity, so the dashed line of 0 gives us the one-to-one correspondence. So the scatter plot above that line gives us the galaxies where the AGN are actually outshining their host galaxy in intrinsic bolometric luminosity. So we can see that there's a few galaxies where this does happen. Using the bolometric corrections that I showed you earlier, we also calculated the intrinsic AGN UV luminosities and then used a line-of-sight dust extinction model described in FLARES 2 paper by Vijay and et al., also from last year, to obtain the dust attenuated UV luminosities for FLARES AGN. So I'm showing here the dust attenuated UV AGN luminosity functions in dotted lines, as well as the intrinsic UV AGN luminosity functions in dashed lines, and the dust attenuated host galaxy luminosity function in solid lines. So we can see that the dust attenuated AGN do not actually contribute to the total luminosity functions anymore. But I'm also including the extreme case of a completely obscured AGN in the intrinsic UV luminosity function. But we can still ask the question, do the AGN outshine their host galaxies in dust attenuated UV? And the answer is not really. There's still a handful of galaxies where this happens, but mostly they don't. And there's a few reasons for this, and the main one is that the FLARES galaxies, the very massive FLARES galaxies, are quite compact, with especially the dust centered around the center of the galaxy, where the AGN is. So the AGN gets more attenuated by dust than the stellar particles elsewhere in the galaxy. And this is why, compared to the host galaxy luminosities, the AGN luminosities are quite a bit lower. And also, we've only considered a single line of sight for the attenuation, so there might be some variation if we considered multiple sight lines, and this is something that will be for future investigation. So FLARES does cover the regime, luminosity regime, where AGN are starting to outshine their hosts, but doesn't yet really probe where the AGN start to dominate, for instance, the bright end of the luminosity function. And on this point, FLARES 2 suite of simulations are currently in development, and they're based on improved physics models as well as better hydrodynamics codes, and will simulate an even larger effective volume. I've also started to look into the ionizing photons produced by the AGN in FLARES. So I'm showing here the in solid lines the median AGN ionizing photon production efficiency, and in dashed lines the median for the host galaxies, and again the shaded regions give the central 68th percentile ranges. So even though the AGN aren't very luminous in the UV, they still produce ionizing photons quite efficiently. The investigation on how many photons they actually produce compared to, for instance, the host galaxies is still under investigation. So stay tuned for the eventual paper on this project. And finally, some very early results from studying the impact of AGN on their host galaxies. So we also have a matched set of simulations where we've simulated a few regions with AGN feedback turned off, and and simulated the same region with AGN feedback turned on to investigate how much that actually affects the host galaxies in those regions. And this early results shows that, well, I'm plotting here the again the median of the specific star formation rate in the AGN feedback off run divided by the specific star formation rate in the AGN on run, and this relation shows that, especially towards lower redshifts, there is an increase in star formation in the simulations without AGN feedback. So it's quite an interesting result in terms of AGN quenching the star formation in galaxies. So work on studying the AGN impact will continue and will be discussed further in the upcoming paper. And speaking of upcoming papers, I wanted to highlight a couple of papers by other authors, from upcoming papers from other authors in our group. So here's an example from William Roper et al. Paper on the sizes of galaxies in FLARES. So what he's showing here is the size luminosity relation for various redshifts in FLARES, along with some literature comparisons. And the other paper that I wanted to highlight is by Chris Lovell, and it's on passive galaxies in FLARES. So on the left here, we see the prediction for number densities of passive galaxies in FLARES up to about redshift 8. And on the right, we see the star formation rate and how it evolves in a single galaxy in FLARES towards lower redshifts, as well as the accretion rate in orange. Sorry, the star formation rate given in the blue lines or the blue histogram, and the accretion rate of the black hole in that galaxy given in the orange histogram here. And interestingly, the accretion almost happens in a single event in this galaxy that coincides with basically dropping off of the star formation rate. So stay tuned for those two papers coming up in the near future. And that brings me to the end of my talk. So hopefully I've convinced you that FLARES is well positioned to study these rare objects in the high redshift universe, for instance the AGN. And I presented some numbers and properties for FLARES black holes and AGN, as well as the contribution of AGN to luminosities of epoch of reionization galaxies, as well as the ionizing photon production. The effect of AGN on their host galaxies is still under investigation, but once that's ready, all of this will be folded in an upcoming paper. I thank you for your time.